with this very good.
Yeah. Good afternoon, all. So we have.
Good afternoon, sir.
Yeah, we have Dr. Samudra Vijaya K. So he has carried out his research in the area of speech signal processing at Tata Institute of Fundamental Research, TIFR, Mumbai. So almost for 3 decades, he has a vast experience as far as speech recognition, and the corresponding allied fields. So later, he went as he also worked as a visiting faculty at IIT Guwahati during the period of 2016 to 2020. Currently, he is an adjunct faculty at IIT Dharwad and at NMIMS Mumbai. His primary research interests area are in automatic speech recognition and spoken language resources. So today he'll be talking about the overview of automatic speech recognition. So all 3 talks are in sequence. So one talk will actually augment the other one. So likewise, that is how we had planned. So now this talk will go a little deeper into the automatic speech recognition itself with reference to statistical models. So we are fortunate to have Samudra Vijay sir here, and thanks for him to accepting our invitation. With that, over to you, sir. Please.
Thank you, Dr. Deepak and Dr. Adi, for inviting me here to share some of the thoughts on automatic speech recognition. Good afternoon, everyone. Today is the first day of this FDP on artificial intelligence for speech and biosignal processing. So this is AI for speech processing and biosignal processing. The first part of this series of talks will be on speech processing, which will be followed by biosignal processing. In speech processing, there are several applications, and one of the applications of speech processing is for speech recognition. And speech is recognized by computers. It is called automatic speech recognition, or ASR. So this is the third talk in this series. In the morning, we had an excellent talk overview by Professor Prasanna on the speech signal processing from machine learning perspective. He gave an overview of various applications of speech processing: speech compression, speaker recognition, and speech recognition, speech synthesis, and various other applications. And he gave an overview of that aspect. Then this was followed at 11:30 by a talk by Dr. Matthew. He talked about the progress of ASR, automatic speech recognition. That is the topic. Progress of ASR methods. He started with the knowledge-driven methods, and then he led up to the data-driven methods. Knowledge-driven methods, where the knowledge of the speech signal is very much used to achieve the task. What was the task? The task was automatic speech recognition. In common parlance, it is called speech to text. Speech to text, automatic speech recognition, voice recognition is another topic, term that is used by ordinary people. So he talked about the knowledge-driven approaches and sort of led up the data-driven approaches. And he specifically dealt with the recognition of pattern recognition. They spent a lot of time on dynamic programming aspect of the speech recognition. The dynamic programming is dynamic program is a computational efficient way of recognizing sequences. Let me put it that way. Speech is a sequence of sounds. When I said the word speech, it contains s, p, u, ch. There are 4 sounds. So it's a sequence of sounds. A word is a sequence of letters. Written language, a word is a sequence of letters. Spoken language, speech is a sequence of sound. So sound recognition of sequence can be done much more efficiently using dynamic programming. He talked about that extensively in the morning. So what I will do is to take up that stream. Prasanna sir dealt to significant extent on signal processing, and Dr. Matthew talked about models for sequential pattern recognition, emphasizing on dynamic programming aspect, the computation efficiency way of doing it. He talked about dynamic time warping, and he also dealt with the hidden Markov model and hidden Markov model. He wrote, he was more quantitative. He wrote specific equations that help us to achieve the task. So he went in that sense fairly in depth. What I am going to do today is slightly other way around. I want to emphasize more on the concepts. My emphasis is on statistical models for speech recognition. Why statistical models are needed or useful? In what way they will be useful? What sort of inspires or motivates us to use statistical models? I will talk more on that conceptual level. I will leave the Dr. Matthew has already dealt with some details. I will leave the details. There are equations, derivations, and so on. There are excellent blogs, textbook chapters freely downloadable, and videos on this also, extensive videos. So I'm going to emphasize on the basic concept. So that would be the first part. And the second part is also to do with the language model. Speech is not any sound. It is not music. It is spoken language. There is a definite order in which these sounds have to come, definite order in the words, and these are language dependent and so on. So we need to talk about the influence of the language or the utilization of the information about the language that a person is speaking for the task of automatic speech recognition. And the last 15-20 minutes, I will also give a glimpse of the latest models which deal with the deep learning. Deep learning was alluded to by Professor Prasanna in the morning, and Dr. Deepak will deal with the sequential pattern recognition using sequential models specifically, and going all the way up to the latest models. So I'm not going to talk about that, but I'll just give a few slides to distinguish between statistical models and the so-called deep learning model. I shouldn't say distinguishing, comparing, and so on. And at the end, I'll also show you some slides about linguistic resources useful for speech recognition. That is the outline of my talk. What is speech recognition? Why is it useful? Because we would like to interact with the machines, and you want to use my mobile phone, I want to use my mobile phone, and I want to say Google Voice search. I speak, the speech is converted into text, and that information, the ASR system not only converts the speech into text, but it also understands what I am asking for, what is my intention, what information I am seeking for, and it gives me back the information. So it's a complete voice-enabled interaction between machines. So it involves speech recognition, one. Secondly, speech understanding my intent. And third is giving back information either in text form or in speech form. Again, text-to-speech synthesis, PCS also comes into play. We will be dealing with only the first aspect, speech to text or automatic speech recognition. And what is speech? I have some thought in my brain and I choose a language, human language. But there are other languages also. I can convey in other languages like sign language without speaking. People do that, but I'm talking of speech, spoken language interaction. I choose a language, in this particular English. I form a grammatically correct sentence so that you can understand it well. So the sequence of words, sentence is a sequence of words. I speak using my articulators. Out of my mouth comes the speech waveform. This is a speech waveform. From this speech waveform is given to the automatic speech recognition system, and it does some processing of the speech is a signal. It processes the signal, extracts some features that are useful to identify different speech sounds, and tries to recover the symbols. My original symbols was S1, S2, S3, etc. It tries to recover the original symbols. So the idea is in my head to begin with. It is that information is encoded in a speech waveform. It is encoded. And the speech recognition system, ASR system, tries to decode it. So ASR is also called decoding. Speech recognition is also called decoding. Encoding when you generate the speech, decoding when the speech is converted into text. Recognition is a pattern recognition, speech recognition of a sequential pattern, but it is a pattern recognition. In pattern recognition, you can think of it as consisting of three blocks. The first is the input signal is processed to extract features that are relevant for the task. In our case, the task is to recognize different sounds. So if I want to recognize different sounds, I need to know how to distinguish between confusing sounds. So I need to extract those features which will help me in distinguishing similar or confusing sounds, such as pa or pa. A little bit of aspiration, pa, pal, pal, meaning changes. So I need to do the signal processing. It was already dealt with in the morning. And then we will have a model of each speech sound. So there will be two phases. One is called training, which is model building. Other is called the testing phase, which is the usage of the ASR system, where we use the new input, new speech wave comes. Signal processing module is same. Features are extracted, and the sequence of features are more matched with each of the sound models of each of the sound, and finds out to which sound model this new speech, test speech, is closest. So there is a pattern matching in all the testing phase. I talk about model. What is a model? Model is a description of a phenomena, preferably quantitative, so that we can do some computation and we can do some inferencing, hypothesize. In our case, our inference is some speech waveform comes. We won't say whether it is a, e, u, a, o, or ka, cha, ta, da, pa, and things like that, or which word it is. That is the inference that you want to do. Therefore, we need a model, a mathematical description of property of different sounds, and that is a model. So, speech. So this is the speech waveform. You see that up to here is a time waveform. Time along the x-axis, amplitude positive or negative along the y-axis. Up to here is silence from here to here. The first, let's say 80 milliseconds. This is in 200 milliseconds. The time is in millisecond. Up to around 70 milliseconds, it is silence. Then there is a tha sound. This is the word tirua. So the tha sound here, and then e sound is here. Ra is here from here to here, and u and so on. Now, if I see ta and other sounds are distinction, that I can see. But look at this vowel. This is the word tirua. This is vowel t. This is u. E and u, they appear very similar. Therefore, so if I want to distinguish between these two sounds, I want to extract features that help me to distinguish these sounds. Just time level information is not sufficient. That's the first point. So we do the frequency analysis. That's the first point. Second point is sound is a sequence of this speech is a sequence of sound. Therefore, it takes short durations of sound, and we distinguish that up to here it is silence, then it is ta, then it is e, ra, 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 u, and so on and so on. We continue to do that. So this is short time processing. This is already talked about it. Typically, we take a short segment of speech of duration 25 milliseconds, and successive frames are shifted by 10 milliseconds. So what features should we extract? Because looking at the waveform, this is the vowel E from here to here. The vowel U appears very similar. So what features should we extract? What kind of signal processing should we do? This is where acoustic phonetics comes into picture. Phonetics is a branch of linguistics that deals with the speech sounds. Phone is a telephone. Telephone is phone, speech at a distance. Tele is distance. So telephone. So phone is the basic unit of sound. Study of speech sounds is called phonetics. And there are three branches of phonetics: articulated phonetics, how sound is produced; acoustic phonetics, that is how the different properties of different sounds are different; and auditory phonetics, how the speech sounds are perceived by human beings. So let us look at the articulatory phonetics, how speech sounds are produced. We already looked at similar diagram. If I want to say an vowel, so the speech is a signal. It requires energy. Where does the energy comes? It is from the air pressure in the lungs. When I want to say a vowel, let's say ah, what I do is my air comes out of my lungs, my vocal folds open and close, puffs of air comes, and the vocal folds open and close periodically at the period of, let's say, 100 hertz. In my case, my pitch frequency is 140 hertz. So 140 pulses come per second, pulses of air comes per second to this cavity, air cavity, which is throat cavity, mouth cavity, oral cavity, and also nasal cavity. Sometimes sound comes also from the nasal. Sound comes from the nasal. These three cavities, throat, oral, and nasal cavity, collectively are called vocal cavity. Why vocal? Because it generates voice. Now, when I want to speak different sounds, I change the size and shape of this vocal cavity. Let me repeat. When I want to say ah, say look at, when I say ah, my jaw is lower. The height of this air cavity here is higher. Ah, E. When I say E, my jaw goes up. So the height of the air cavity is lower. When I want to say ooh, my lips protrude out. Ooh. So the length increases. So different sounds are produced by changing the size and shape of this vocal cavity. When size and shape changes, the air cavities, when they are left on its own, when the glottis is closed, vocal folds are closed, the air molecules that are vibrating in the vocal tract, they go into resonance because they are not disturbed by others. They go into resonance and vocal. Just a minute. They go into resonance, and the resonance characteristics of different sounds are different because the size and shape of the vocal cavity is different. So the sound comes out here, and that sound, suppose you are speaking at a distance, that sound travels through the air, through a medium, and reaches my ear, and air sound waves go through the outer ear, in middle ear, series of three bones, and inner ear. The cochlea, the snail-shaped structure, and the cochlea does a signal analysis. What kind of signal analysis does it do? It turns out that this cochlea does the frequency analysis. Why? Look at the waveforms here. Waveform of this sound E and vowel U, they appear similar. And over the evolution, animals, including human beings, have heard that have learned that it is better to do the frequency analysis. So what kind of frequency analysis the human cochlea does? So there is the human cochlea, this cochlea, if you stretch it out, it has it's a fluid-filled chamber. There are actually three chambers, and there are two membranes separating the three chambers. One such separating membrane is called basilar membrane. And that basilar membrane actually does the frequency analysis. So how does it do the frequency analysis? The basilar membrane is about 30 millimeter long. 30 millimeter, 3 centimeter, little more than an inch, little more than this. Okay? 30 millimeter long basilar membrane is connected with 10,000 neurons, about 10,000 neurons. And different parts of the basilar membrane respond maximally to different frequencies. So the different parts of the basilar membrane act like band pass filters. And there are 10,000 nerves. Each of the nerve actually sends information about a small band of frequency centered at certain frequency. Human auditory range is 20 hertz to 20,000 hertz. There are 10,000 neurons which essentially basilar membrane does the frequency analysis and sends impulses through these 10,000 nerves to the brain, and brain figures out, oh, there is more energy at 1,000 hertz and at 2,200 hertz, therefore this must be vowel E. This is a kind of recognition that the humans, how they perceive the sound. There is an animation of such a cochlear animation. I showed the link there. Let me play it out because it gives a good feeling of this. I am hoping that you will be able to hear the sound. To begin with the first 30 seconds, there is no sound. It is just an animation, quiet right now. So it's going to the cochlea. You see this snail-shaped cochlea here. Now it's stretched out. Now this 30 mm basilar membrane. Now it sounds will begin. Can you hear the sound? Somebody can respond. Could you hear the sound? Can anybody say?
Yes, sir.
Okay, thanks. I just wanted. Okay, so let's start with the 3 monotones to begin with: low frequency, mid frequency, and high frequency. You notice that different parts of the basilar membrane respond to different low, mid, high frequency. And when there is all the 3 tones are present, then multiple neurons send impulses to the brain. Okay, it is just an animation to show that the cochlea does this kind of animation, and it does the Fourier analysis. So let me stop this. Okay. So yeah. Okay. Now let me share this tab. Oh, it is still showing the other one. Stop presenting. Let me start presenting the new one, that tab. Yeah, okay, it is. Okay. So so people also did such kind of filter bank processing. This is called capsule analysis. Professor Prasanna talked about it in the morning, and it so happens that although the 30 millimeter long human basilar membrane is analyzing 20 hertz to 20,000 hertz, it gives more emphasis, or more it analyzes low frequency sounds with the higher frequency resolution than the high frequency sounds. Or out of 10,000 nerves connected to 30 millimeter of basilar membrane, half of it, or 50%, analyzes only frequency up to 22,000 hertz, 20 to 2,000 hertz. So information in the low frequency, 20 hertz to 2,500 hertz, is given analyzed with much more vigor, and higher frequencies are analyzed by the rest of the 50% of the 10,000 neurons. Why is it happening? Because most of the sounds have distinguishing characteristics, resonance frequencies in this range. So this scale, nonlinear scale, is called MEL scale, and similar processing has been done by EC engineers, and this is called MEL filter bank processing. And the features that characterize different sounds, popular features are MEL, frequency capture coefficient. This block diagram also you saw in the morning in Prasanna's talk. So signal processing, suppose there is a 1 second of speech, you take short segments of speech and generate MFCCs. MFCC coefficients, typically 13 MFCC coefficients are computed. So a 13-dimensional feature vector is generated every 10 milliseconds. In other words, if there is a 1 second of speech, then there will be 100 feature vectors, each feature vector of 13 dimensions, MFCCs. In fact, you can also compute the slope and curvature, in which case delta, double delta MFCCs, it will be 13 dimensional feature vectors. But that is the signal processing that is most popular one. However, you see this one in 1 millisecond, you see the dots there, they are the samples. If you see 1 second of speech, as you see here, it considers several sounds. The sounds vary with the time in 1 second. Therefore, the spectral properties also vary. So I want to see the spectral property as a function of time. In other words, I want a time frequency representation of speech, not just time representation of speech waveform. Time representation of speech waveform is shown here, okay, on the top one. Whereas the bottom one graph shows a time frequency representation. It is called a spectrogram. You might have heard of ECG, EEG, electroencephalogram, and something. Gram is anything that is a function of time. So signal function of time, in this particular spectrum as a function of time. So on the x-axis is time. You see the time here, 100 millisecond, 200 millisecond, and so on, up to some 800 millisecond. It's about 1 second long. And this word that was spoken, time waveform, is shown here. The word is Thiruvananthapuram. North Indian spoke it. He spoke as Thiruvananthapuram. And the corresponding locations of the different sounds are shown here in this graph at the bottom. And you see that the vowel E has spectrum characteristic here, because the y-axis is the frequency and intensity shown in color coded. You have seen the spectrogram, so I'm going to run through this quickly. So the vowel E is from around 70 millisecond to 120 millisecond. It has resonance frequencies here, 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 and so on. First resonance frequency F1 is here, second resonance frequency F2 is here, and so on. Vowel O, you see its resonance frequency is different. If you look at the time domain waveform, E and U, they appear very similar. But if you go to the frequency domain, their characteristics are different, their resonance frequencies are different. This is the advantage of frequency analysis. Engineers call it as a spectral analysis, physicists call it as a Fourier analysis. The ordinary people call it as a frequency analysis. So there's an advantage in going to frequency domain. It's another representation. Dr. Matthew talked of various kinds of representation. Frequency domain representation is one of them. Kestrel domain representation another. There could be wavelets and various representations. Right now we are looking at spectrogram, which is a representation of the speech signal, not only in the time axis, but also in the frequency axis. All right. So we have done the signal processing part. Now let us look at the model generation. Now, what kind of models should we have? Well, A is A. What's the difficulty in recognizing A from A or E or U? They are different. But so why can't we use a template matching method? As Dr. Matthew told, he talked about instance-based models. A model is kept. Suppose you are talking of recognizing handwritten characters. Capital A is like this and a horizontal line. It's how it is. But different people, when they write, the capital A's written by different people are different. And even A written by me at several times will be different. Similar things happens in the case of the speech. even the speaker dependent variations and intra-speaker variation within the one speaker variation depending on the mood, his voice quality changes. Therefore, the properties of the speech changes. One of the property that speech changes is because of the physiological differences. What is physiological differences? Suppose I say ah, and I ask my grandniece, she is small, she is 6-year-old, she is shorter than me. So if I ask her to speak ah, she will say ah, but it sounds slightly different. It's not just due to the pitch, which does change, but also because of the physiology. What is the physiology change? She is short. She is 3 foot long. I am 10 feet, 6 feet tall. She is just 3 feet tall. Therefore, her head size is also half of my head size. Therefore, the length of the resonant cavity of my grandniece is half of mine. And resonant cavities depend upon the length. Resonance frequencies are inversely proportional to the length. Therefore, even though she also says ah, the resonance frequencies, as you see in the spectrogram, this frequency location will be different for my grandniece than for me because her head size is smaller, her vocal tract length is shorter. So let us look at this kind of resonance, that the resonance characteristics depend on the length of the vocal tract. This can be illustrated by an animation. Let me play a music here. Okay, I am sharing this tab. I think, yes, you are able to see it. Let me play it. So I'm going to play the first 35 seconds of this music. It's a music that is played on, it's air blown into tubes of different lengths. Let's play it. So did you notice that when he played on the longer tube, resonance frequency was lower, low frequency. Let me play it again, that part. Low, medium, high frequency, shorter the length. That's the point that I wanted to make, that the shorter the length, higher the frequency. That's the point I wanted to make. And therefore, the ah spoken by different people will have different resonance frequencies. For example, here is the spectrum, amplitude, magnitude as a function of frequency shown for the same vowel E in the same word pin spoken by male and female speaker. See, the male speaker, his head size is larger, therefore resonance frequency is smaller. Female speaker, her head size is slightly shorter, therefore resonance frequency is higher. Therefore, there is so these resonance frequencies are also called formants. Let's concentrate on the red curve. This is the first resonance frequency. It's called a formant, first formant, or denoted by capital F1. This is the second resonance frequency where there is a peak in the spectrum, and that is called F2. This is called F3, third formant, and so on. In fact, people knew this, that resonance frequency change with respect to vocal tract length, because there's pure physics, and people have measured the resonance frequencies or the formant frequencies of different songs. Here is a famous diagram by this is done in 1950, mid 1950s, nearly 70 years ago. Peterson and Barney published this paper in Journal of Orchestral Society of America, where they asked 100 people, both adult male, adult female, and children, to speak different songs, different vowels. They had 16 vowels, and see the vowels here. There's a vowel A here. Can you see an A here? A and E and U. Here. So you see that, and what is plotted here is a resonance frequency of the first format. First resonance frequency is plotted on the x-axis, and the frequency of the second resonance, or where the second peak occurs, is printed here. For example, if I look at an oval E, its first format frequency is around 300 Hertz, and the second format frequency around 2500 Hertz. Yes, let's look at the first format frequency around 300 Hertz. Second format frequency around 2300 Hertz. So these two values of the oval E is 1 point here. And so there are 100 people, therefore 100 points. What you see here is, this is the beauty, that different ovals have different resonance frequencies. Therefore, if you just use two features, frequencies of the first two major resonances of the vocal tract, then we seem to be able to distinguish between different ovals. Well, but what I noticed that although I said E, the male person speaking E, their resonance frequency is here. A female person speaking the vowel E, their resonance frequency is slightly here. Children, their head size is smaller, therefore resonance frequency is very high. Therefore, although we think that E is a single sound, its resonance characteristics are different. Therefore, there is a spread of the data. It is not just one data dot, it is a spread, or each vowel is a cluster of data points. It is not fixed. There is variation. There is variation in the character of every vowel. Whenever there is a variation, we resort to statistical model. What is statistics? Data analysis is a new term. Analysis is the description of the data. In the data, in this particular data varies, therefore we describe it as by two quantities typically. One is center of the cluster. Center of the cluster E is here. Center of the cluster I is somewhere here. Center of the cluster U is somewhere here, and so on. That's one. Second, the amount of variation around the center. For example, if you look at this center oval E, its mean F1 value, first format frequency, around 300 Hertz. And it can vary between 200 Hertz to 400 Hertz. So the variation is, so we can say that for the oval E, the frequency of the first resonance, or capital F1, is 300 plus or minus 100 Hertz. So 100 Hertz is a measure of the spread, typically measured by standard deviation. Standard deviation is square root of variance. So the variance along the x-axis or the F1 axis is lower as far as the vowel E is concerned. But look at the y-axis. It varies almost from 2000 Hertz to 3500 Hertz. Variation of plus or minus 700 Hertz. So the variance is also depends upon the frequency characteristics. It is not a circle. This shape is not a circle, but similar to oval shape. But we can describe it by a statistical model, mean and standard deviation. Typically denoted by mu and sigma. Mu for mean symbol, Greek letter sigma for standard deviation. So we can use the mean and the standard deviation optionally to measure the distance of a test data point to the centers of the two clusters and assign this data point to either this cluster or this cluster depending upon the distance. If we just use mean distance from the mean without using the standard deviation, this data point will definitely be assigned here because this distance is smaller than this distance. But if you consider the standard deviation, that the blue circle, blue ellipse is very much spread, lot of variation here, this data point will be assigned to this class. So whether a test data point belongs to the blue, is assigned to the blue class or the red class, depends upon the distance measure that we use. Whether you use a simple Euclidean distance or a weighted Euclidean distance. Obviously, this is better because it also takes into account the shape or the spread shape of the cluster or the spread of the data points around the center of the cluster. But is that good enough? this statistical model is not good enough. Why? Let us look at this particular point. Clusters here. There may be an or of the word college, or spoken by child, or as spoken by an adult. As spoken by an adult will be on the lower end, or spoken by child will be at the higher end of the O. So this data point, there is no way you can definitely say whether it is or a, because this data point could be an or spoken by a child or as spoken by an adult. Remember that adults will have lower resonance frequencies and children will have higher resonance frequencies. Because there is overlap of the clusters, our simple statistical model based on mu and sigma, mean and standard deviation, is not good enough. Therefore, we cannot make definitive data. We cannot classify the data point either here or here, but we can make a probabilistic statement or the chance that it belongs to either this class or that class. That brings us to a version of the statistical model, probabilistic model. Probability is a sub-branch of statistics. So when we talk of probability model, we talk of probability distributions. And one of these common distribution is a Gaussian distribution, also called a normal distribution, characterized by the mean mu and the standard deviation sigma. This probability density function is given here because x is a continuous variable. It's a density function. This is not probability, it is a density function, probability density function. So what we did in the case of statistical model, we use a distance measure and classify the test data point either here or here. We use the distance, whereas here we are going to use the probability, but it is not the standard probability that we are used to. It is so-called conditional probability. What is conditional probability? Take a data point here. Let's take an x-axis along the one feature. Let's say second formant frequency is along the x-axis, and second formant frequency one oval is smaller. Second formant frequency of the another oval, blue oval, is larger. So the green oval has a lower mean, and blue oval has the, I'm saying blue oval just for the illustrative purpose, blue oval has a higher mean. Consider a data point somewhere here. Then this has a small chance of being a green oval, but a larger chance of being a blue oval. Oval belonging to the blue oval class. So this probability, no, these two probabilities do not add up to 1. It can add up more than 1 also, because what we are saying is, what is the chance that this frequency, the value, is generated by a green curve spoken by a child, or the blue oval spoken by an adult. So it's always, we say green oval, we begin. What is the probability that green oval can generate this frequency, or what is the probability that the blue oval generated this value? So we always assume that what we compute is not the ordinary probability, which is called the prior probability, but class conditional probability. Suppose the data point here belongs to the green class, we characterize by mu k and sigma k. What is its probability that it belongs to this class? That this green class generated this format. Similarly, you can also compute the probability that the blue class generated the same format value. So we start with the class and we compute the probability. So we start with the class, and there is a vertical bar here that we already assume that it belongs to the green class. What is the chance that the formant frequency is 2000 Hertz? So this is class conditional probability. It is not a priori probability, it's a conditional probability, also called likelihood. So we compute this class conditional probability of the test data point correspond to each of the 50 or so speech sounds in the language, and assign the data point to kth class if the class conditional probability is of the kth class is higher than class conditional probability of all remaining classes. Remember, when we are talking about simple statistical model, we assign the data point to the class which has the lower distance. Whereas in the case of the likelihood, we assign the data point to that class whose class conditional probability is higher. Distance is lower, conditional probability will be higher. Therefore, the criterion of classifying a data point based on maximum likelihood, maximum class conditional probability is called maximum likelihood classification criterion, or ML. ML criterion, you will quite often see this ML as an acronym, maximum likelihood criterion. Now, okay, we went with probabilistic model, will it be good enough? What does this say is that the probability distribution is said to be Gaussian, which has a single peak, which is symmetric. But if this is the case of the single dimension, if you go to two-dimensional space, then it assumes that Gaussian distribution is oval-shaped. Oval-shaped, why? Because variance along the x-axis may be different than the variance along the y-axis. That is okay, but Gaussian distribution always assumes the oval shape in the two-dimensional surface. But let us look at our F1, F2 diagram. Well, this is nearly oval, all right. But let us look at some oval like A. A is the basic sound. In our Aksharamala alphabet, A, I, E, A is the first sound. Look at the shape of the cluster of the sound A. It is not oval. It is bean shaped. It is not oval. Therefore, if you assume that the shape of this A is oval, it is a poor approximation, poor model. Can you do better? Oh yes, we can do better. How? What will assume that this shaped structure is a mixture of two ovals. Mixture of two ovals. What are the ovals? One oval which is slightly vertical, like this. Please follow the pointer. One oval slightly vertical oval and another oval slightly horizontal oval. So if I describe this entire shape as one horizontal oval and one slightly different oval, but placed at slightly different places, their mu1 and mu2 are different and their orientations are different. The ellipse orientations are different. Then we can model this bean-shaped cluster as a mixture of two Gaussians. Such a model is called Gaussian mixture model. Do we actually need it? Well, here is a histogram of one capital coefficient of a phone. One sound, one capital coefficient. You see that histogram has multiple peaks. Therefore, if you approximate by a single Gaussian, very poor. On the other hand, if you approximate this histogram of one capital coefficient of one phone as the summation of several Gaussians, then this curve represents this histogram better than the distribution curve of a single Gaussian. Therefore, we need mixture of Gaussians, several Gaussians, collection together. That such a model is called Gaussian mixture model. And so the Gaussian mixture model can represent multiple peaks, asymmetric distribution, and so on. This is the Gaussian mixture model classification. We again use the maximum likelihood classification criteria in the case of the Gaussian mixture model. How do you train a Gaussian mixture model? Let's say we have just two. There is an algorithm. It's called IIIT algorithm. The general name is expectation maximization algorithm. It's not estimation. It's expectation because probability distributions are involved. Expectation of a quantity is involved. It's an IIIT algorithm, and it uses the principle of gradient descent. There are two steps. One is expectation step, E step. Another is called maximization step. I don't have time to explain that. What I will do is to explain it using an illustration. In USA, let me just see whether there is any question so far. No, thank you. Let me continue. In USA, there's a national park called Yellowstone National Park, and there is a geyser. Geyser means water spurting out of the earth. and water spurts out, it starts spurting out, goes up, 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 up. Water keeps coming out for a few seconds, 30, 60 milliseconds. So the duration of how long it will water keeps coming out is shown on the vertical axis here. And then it stops. And then it waits for several minutes, 3, 4, 5 minutes, and then it again starts coming out. So it's a periodic phenomena. So you can measure the time interval between successive eruptions of the water and the duration of the eruption. The time interval between the successive duration is shown on the x-axis, and the duration of the eruption itself in minutes is shown along the y-axis. So the data points have been collected over centuries, and here are the data points. If you see here, if I want to fit a straight line, I will have to fit a bent straight line, but that's okay. We want, what you see here is that these data points do not seem to belong to a single cluster. There seem to be two clusters. One cluster here, another cluster here. I'm talking about natural phenomena, one phenomena, but still it seems to be two clusters. So a single Gaussian distribution will not be good enough model. Here, can you model it as a mixture of two Gaussians? Model this particular data, model this data as a Gaussian mixture model with the two mixtures. So I'll illustrate how such a Gaussian mixture model is trained. To begin with, this is called K-means training. To begin with, you pick up random points as the initial means of the two clusters. Here, initial mean of the yellow one cluster is taken here, another cluster center is taken here. They are very close by. They seem to belong to the topmost part. Doesn't matter. And variances are taken, unit variance, similar variance. Now, the iterative algorithm that I talked about here, expectation maximization algorithm, adjust the mean, mu1 and mu2, and variance iteratively using the gradient descent algorithm that I talked about, which will increase the likelihood of the training data. Let us look at an animation. See, slowly the means are changing, and even the rotation, the shapes are also changing. So look at the red curve, red axis. Initially it was flat, then it becomes flat, it is rotated, and then it became vertical. It matched the two shapes of the two clusters. So this is one way of training. This is the expectation maximization algorithm, which illustrates how a Gaussian mixture model with the two mixtures are trained. You can do with the same mixture, any number of mixtures. Okay. So far, we talked about training. I have to go a little quickly. Training one data point. We need to recognize a sequence of data points, because speech is a sequence of sound. We need a sequential pattern recognition. And speech recognition is difficult for various reasons. I talked about speaker specific variations, and background noise may change. And there is one which is called phonetic content. I want to illustrate that because that will motivate us to why we need to use a hidden Markov model. Let us look at this spectrogram. Time along the x-axis, frequency along the y-axis. The sound that was spoken was Thiruvananthapuram, but actually Thiruvananthapuram. And notice, and let's look at the vowel U here. U, if I look at the waveform, it is from here to here. From somewhere around 140 millisecond to somewhere around 210 milliseconds. Vowel U has its first resonance frequency is around 500 Hertz, second resonance frequency is around 1500 Hertz, third resonance frequency, and so on. Okay, now what is the vowel U? Vowel U from around 140 millisecond to 200 milliseconds is one sound U. But notice its second formant frequency. Initially, second formant frequency are around 1700. And at the end, when U ended, its second formant frequency came down as much as 1300. So what you notice is, from the waveform, it looks from here to here, it is the same sound, except the amplitude has changed, volume has changed, but character hasn't changed. But if you look at the spectrogram, vowel U, second formant frequency decreased from somewhere around 1700 to 1300. Why did it change? Should be the same vowel, no? changed because person is speaking Tirunantapuram, he doesn't say no, he speaks continuously Tirunantapuram. Sounds come one after another, not in digital fashion but analog fashion, continuous fashion. And my articulators don't say no, it's continuously moving. Therefore, even when the person is articulating oo, his brain has already given the signal to the articulators that next sound is wa. So he is already going from oo to wa, opening. Oo is slightly closed lips and wa, his jaw is lower. So the articulator, in my case, jaw and lips are continuously moving even when he is speaking the sound oo. This is called co-articulation. Articulating sound to multiple sounds together. So the influence of the next sound, wa, he has influence on the previous sound that is being spoken right now, oo. So this is called, so articulation of one sound, oo, is influenced by the next sound and previous sound. Look at it. The formant frequency decreases in the case of this oo. Now, any question? No. Now let's look at the next two. The formant frequency is increasing. What is happening, boss? Either, firstly, first point is oo is not constant. I expect it to be constant. Here it is decreasing. Here it is increasing. Why? Because here. Is there any question? No. Okay. Jalraj, is there any question? No, thank you. Okay, thanks for switching off. Okay, so the vowel oo, the formant frequency decreasing here because there is a bilabial sound wa, and formant frequency is started low and increasing here because preceding the oo was a bilabial sound lip position. Therefore, whenever a vowel oo is preceded by a bilabial sound, it will start with a low value and increase to its value. Whereas the oo is followed by a bilabial sound, its formant frequency decreases. Therefore, articulate of one sound is influenced by left and right sound. This is called phonetic articulation, and that brings, this is where the hidden Markov models become relevant. Jalraj, can you please mute it unless you want to speak? Thank you. Some sound keeps coming from your side. Okay. Let me go back. So we will introduce the Markov process, hidden Markov model. I'll quickly introduce and move on because I am not going to talk about it much more. Sign and a signal. This is a sign. This signal is varying. Signal can be of two types: deterministic signal, traffic signal is deterministic. Weather pattern, they are stochastic signal. Today it is sunny. Whether tomorrow will be cloudy or rainy, nobody knows. I mean, even the weather guys predict, but not sure. It is always uncertainty. So signal which has uncertainty is called stochastic signal. So a Russian scientist called Markov studied such stochastic signals, and in this particular case there are three weather patterns: sunny, rainy, and cloudy. He called them as three states of weather. Okay. And he studied this this is a sequence of three states, collection of three states. You can go from one state to another state, weather state from sunny weather state to rainy weather state or cloudy weather state. You can go from anywhere to anywhere. It's kind of weather going from one part of the chain to another part. He called it as a chain, and it has come to be known as a Markov chain. And Russian scientist in 1913, more than a century ago, studied such a phenomenon in the case of a text, written language, and he modeled it as a random sequence. He called it, and he studied it, that's why it's called a Markov chain. In our case, we talked about oo. The oo is decreasing, the second form of oo is decreasing here because there is a bilabial sound, right? Whereas in the case of oo, it is second form is increasing because bilabial sound occurred earlier to the left side. Now let us look at another vowel a here. A, for example, its duration is from 700 millisecond to 800 millisecond. Look at the second form of frequency, it is nearly constant, suddenly falls down. Third formant frequency increases and constant. Fourth formant frequency Ardha Chandra. It decreases initially and increases. Fifth formant frequency Ulta Ardha Chandra. It increases first and then decreases. See, so in this particular variations are, all sorts of variations are happening because of the influence of the previous sound R and the following nasal sound Ma. Now, hidden Markov, so we can model it as, so instead of modeling one sound as one unit, what we'll do is this sound here we'll model the 3 units. The middle, so what is shown here is the formant trajectories. Can you see here? The second formant is constant and decreasing. Constant and decreasing. Third formant increases slightly and steady. Increases slightly and steady. Fourth formant is like a Ardha Chandra. It's crescent shape, like this. So if you see this, middle part is reasonably constant. Left part of the sound is influenced by the previous sound. Right part of the same sound is influenced by the following sound. Therefore, it is better to model one sound as a sequence of 3 parts. The initial part or the left part or part number 1, middle part number 2, or third part or segment part number 3. In Markov model, Markov called them as states, state of mind. You know, that's kind of state. It's not Maharashtra versus the Karnataka. It is state of mind. It's in this particular state of the speech sound. So this part is called first state S1. This middle part is called represented by state 2 S2. This part is called state 3 S3. So we model one sound as a sequence of 3 parts or 3 states. Middle state, characteristic of the middle state is reasonably steady, doesn't vary very much. Characteristic of the first state, initial state varies a lot. Characteristic third state, last state also varies a lot. So whenever there's a variation, we represent it by a Gaussian distribution statistical model. So if you look at the F2 of this third state, it is varying a lot. It has a mean value here and a variation. So you can fit one Gaussian distribution for this state, one Gaussian distribution for this state, and another Gaussian distribution for this state. So the duration of this oval was 100 millisecond, which corresponded to 10 feature vectors, MFCC vectors. Now, instead of treating this one sound as a sequence of 10 feature vectors, we treat it as a sequence of 3 states. Each state is characterized by one Gaussian distribution, which has its mean and standard deviation. So notice this change from sequence of 10 feature MFCC vectors to sequence of 3 states. And we know that when there is a state sequence, Markov process helps us. So let's go to Markov model. But the problem is, in each of these parts that we are talking about, there is a Gaussian distribution, because there is each of the part is also not constant, there is variation. Therefore, associated with each of the state, the sound is treated as a sequence of 3 states. State number 1, state number 2, state number 3 correspond to 3 parts. Initial part, middle part, final part. But even within the first state, there is variation. Therefore, the characteristics of this first state or the initial part of the sound is also characterized by a normal distribution, Gaussian distribution. Therefore, it has a mean and spread. So, look at this guy. The mean is different, variance is different. Therefore, now one oval is represented by a sequence of states where the value of the formant frequency, which is what we can measure, or which is also called observation. What we can measure is called observation. That value is not fixed, it is changing. Worse, sometimes, so let us look at this value. This value can come from the state 1 or from state 2. Therefore, given a value, we cannot tell whether it came from state 1 or state 3, because the same state can generate 2 values. Look at this F3 here, or look at this F4 here. See, It is high here, it is also high here. Just because F4 is high, we cannot say whether this F4 belongs to state 3, S3 or state 2. It doesn't belong to state 2 because state 2 value is lower. Whether the high value belongs to S1, state 1 or state 3, that we can't say. So just by measuring the formant frequency, we cannot say whether it belongs to the initial part or state 1 or final part or state 2. Or by measuring, by observing something, we cannot tell specifically whether it belongs to the initial part of the vowel or the later part of the vowel, or which state it comes from, which state it belongs to, which state generated this particular observation. Therefore, the state identity of an observation is not known, or it is hidden from us. What we observe is what we measure, formant frequency. What we do not know is a high formant frequency belongs to state 1 or state 2. Or state identity is hidden. A Markov model where we can see sequence of states, state 1, state 2, state 3, but by measuring, by observing something or measuring something such as formant frequency, we cannot tell whether it came from state 1 or state 3. Such a model is called hidden Markov model. Markov model is a sequence, it's like this. There are a sequence of states, but in addition, if the sequence of each of the state is also characterized by a probability distribution and there is overlap between the probability distribution such that given an observation, formant frequency, we cannot tell whether it belongs to S1 or S3, then state identity is hidden, or therefore such a model is called hidden Markov model. And this phenomena happens even in the case of the vowels. Let me look at the F1, F2 diagram. If I go to the F1, F2 diagram, a particular point, for example, here, does it belong to A or does it belong to A? That is not known. So just by measuring one data point here, that the F1 is 700 Hertz and F2 is 1000 Hertz, we cannot tell whether it is A or A. Whether this data point is A spoken by a child or A spoken by an adult. The identity of the speech sound is hidden from us, or the phone identity is hidden from us, and it's a chain of states. Such a model is called a hidden Markov model, and the word hidden comes because by knowing an observation, we cannot definitely tell whether it was generated by this state or this state, or the state identity is hidden. And there are parameters. I'll just skip that because I'm running short of time. So what is the use of hidden Markov model? Suppose you have to build a model. We'll come to how to train the model later, last. Suppose you have a trained model. Dr. Matthew talked about name dialing. I want to call Dr. Matthew. What I'll do, I'll use my mobile phone. I'll press the button and I say Matthew. It dials Matthew. And I want to call Deepak. I say Deepak. It calls Deepak. So how does it do that? Because it has stored the patterns of the word Matthew or Deepak in my mobile phone. So if such a, and it is generally stored as hidden Markov model. If it is stored, if I have to call 100 people, there will be one more HMM, one hidden Markov model for each of the 100 people. When I say something, the speech is analyzed, MFC is something like that. It is matched using whatever MFC feature vector sequence of whatever I told, speech data that I told, it is matched with each of the models, and whichever model has the closest matching, then that person is called. So this is given an observation sequence, MFCC vector sequence. We want to find out what was the name that was spoken. So that is matching, and there is an algorithm for doing that, or algorithm which also recursion. I will not skip that. I'll skip that. The second problem is, well, this is okay if you have 100 names, but I'm speaking continuously now. There are millions of words. And further, it is not just one word I'm speaking. I'm not speaking with the millions of words. I don't put pause between the words. I speak continuously. There is no well-defined boundary between the words in waveform. Therefore, I want to recognize a sequence of words given 1 second of speech. And in that particular case, I want to, given a MFCC vector sequence, I want to identify the sequence of sounds that corresponds to that vector sequence. Suppose I say Mera Bharat Mahan, it may last for 500 seconds. There will be 50 MFCC feature vectors. So 50 MFCC feature vectors are given. I want to know, I want my system as a model to give me the output of Ma, Hi, R, correspond to Mera Bharat Mahan, sound sequences. That is called finding out the optimal state sequence, optimal words sound sequence given a sequence of MFCCs is called is the recognition part of the recognition. There's an algorithm called Viterbi algorithm. Dr. Matthew talked about this also, similar to dynamic time warping, dynamic programming that he talked about. So generating speech, from the speech signal, you want to generate the word sequence. And then of course you need to see how to train this model. There is an algorithm called Dharwad algorithm. I will not talk about it. So I'm not talking about that because there are beautiful blogs here. There are videos here, YouTube videos are there, textbooks, chapters are here. And specifically this is something that is freely downloadable. I urge you to look at that. I have 15 minutes. So I'll quickly go through the language model. Again, Dr. Matthew talked about it. Speech is spoken language. Not all sound sequences are valid words in the language. If I say M-A-N, man, yes, it is a word. If I say M-N-A, it is not a word in English. So lexicon matters. So the information about the language, syntax, grammatical rules, meaning, common sense, pragmatics, all these are language dependent. Therefore, there is information, language dependent information that is characterized by a language model. And how to combine information from acoustic model and language model? Our goal is, given an MFCC vector sequence, we want the optimum word sequence, and that can be computed using Bayes rule. Dr. Matthew also showed this equation. So this probability is given by the acoustic model. This probability of word sequence is given by the language model, and we want to find out the best word sequence. Therefore, this is a search of various word sequence hypotheses. So I'll quickly talk about the lexical knowledge. A decade ago, I went for a trekking in the state of Mizoram, Northeast India, near Myanmar border. And it was trekking, and there's a tent here. See the name of the camp? It's by Youth Hostel Association India. I can't pronounce it. I wrote it here. Ngal Chong. Nga. This word begins with the sound Nga. This doesn't happen either with the Hindi or Dravidian languages or Indo-European languages. A word can begin with ma or na, but it cannot begin with the Nga. Going. That last word on going. That, whereas Mizo, it's very common. Ngal Chong. So a word can begin with the sound ng is depending on the language. That's the lexical knowledge. Of course, words are pronounced differently. So let us say the word Aj. If you ask a South Indian, Dravidian, right, studying Hindi, he will read it as Aja. You ask a Kannadiga, he will definitely read it as Aja. I did that, but it is to pronounce it Aj. The A at the end of the word should not be pronounced. Then there are geminated sound, BB, double B, Abbas. And not just that, not only the A at the end of the word should not be pronounced, sometimes the A at the middle of the word also should not be pronounced. If you ask a Kannadiga to speak this, he will speak it as Dharwad. But in Hindi, this is Dharwad. Dharwad. The A after the R is also gone. A after the Da is also gone. There can be even worse situations. I'm talking of Pahale. This is what I South Indian will read it, but Hindi guys pronounce it Pehle, although it seems to be written as Pahale. So the pronunciation rules. So this how a word is pronounced has to be written in the form of a phone-like symbols correspond to different sounds, and that is called pronunciation dictionary. Sometimes people also call it lexicon. And even one word can be pronounced differently in different languages. For example, in South Indian languages or in Marathi, this is called Vijnan, Jna, Jna. Whereas in Hindi, it is called Vigyan. The same sound, origin Sanskrit, but pronounced differently in different languages. This all has to be written in the pronunciation dictionary. There's an explanation of the symbols that are given for Indian language. So this is called ILSL, Indian Language Speech Labels. The Speech Recognition Consortium designed this decade ago. It's being used. There are special situations, cases of the Indian sounds, such as geminated sound, nasalization, kaha versus kaha, makes a difference in meaning, and so on. There are characters of different sounds. I want to look at any other one. In addition, there are Tibeto-Burman languages where the sound is same. Depending upon the how I is pronounced, the tone, the meaning changes. There are tonal languages. Here was an example of how speech is recognized, how sound hypothesis is done, and how the grammar is used. I'll skip that in the interest of time. For example, here the word sequences that are hypothesized are, Shashikant Reddy has raised a hand, so let me ask him to. Yeah, please say something. Ask your question. Okay, if you do not have a question, I'll continue. Let me go back here. So, it is hard to wreck a nice speech. No, it is hard to recognize speech. That is semantically correct. Although this word sequence has higher probability, conditional probability, because the way this guy has pronounced it, but this makes more meaning. So not only the grammar comes into picture, but also the semantics, meaning also comes into picture. How the language model is prepared? Well, Dr. Matthew also talked about this n-gram model. It's the ratio of it can be estimated as the relative frequency, and one of the common models that is used is n-gram. That is the sequence of probability of the sequence of n words, and there are some interpolation methods in backup grammar and so on. Still, there can be ambiguities. For example, red and red pronounced same but meaning different. In Hindi, tal, tal, tal rhythm, and the tal is lake. Or prosody pair. Roko, mat jane do. You are going through a gate, and because of COVID, there is a security there. Show me your RT-PCR, otherwise don't go. Roko, the officer says, stop him, don't let him go. On the other hand, officer says, Roko mat, jane do. See, where the pause is meaning completely different. So the prosody also matters in speech recognition. In addition to hidden Markov model, if we talk of hidden Markov model, each state being represented by a Gaussian distribution. Instead of Gaussian distribution, you can also use a Gaussian mixture model. And there are issues with the. So my goal was to talk about statistical model, specifically with the hidden Markov model. There are some various assumptions are made in hidden Markov model, and that goes into. So hidden Markov model is replaced by deep neural networks. And order decreases. Presenters are also showed this graph. And about this deep neural, it uses temporal as it exploits the temporal aspect of the speech signal much better. There is also called end-to-end ASR, so-called encoder-decoder. What I want to spend time here is on some of the assumptions that are made in hidden Markov model, GMM model. This is what is popularly used, and there are several assumptions are made. Sophisticated model, even using HMM, some assumptions are removed using the deep neural network to generate the posterior probability of different sound. Recurrent neural networks and connection is temporal classification. Only one assumption is made. Encoder decoder, even that assumption. So I just look at this table to see how HMM and deep neural network various assumptions are relaxed. Therefore, it takes into account many more variations. Therefore, effectiveness is increased. Okay, 5 more minutes. Spoken languages are needed by speech recognition system, audio files, transcription, pronunciation dictionary. Source of audio files are there for Indian languages, many of them. And toolkits are there, such as Kaldi. That is the toolkit. Somebody yesterday in the morning asked Prasanna sir, which toolkit you want to use. If you have a few hours of data, 5 hours, 6 hours, use Kaldi. If you have large amount of data, then you go for the end-to-end system, such as even Kaldi permits, ESPnet permits. In fact, there are pre-trained models by it's called Vakyamsh. Step is a NGO. It has trained models in Hindi, Gujarati, Tamil, and various languages using 10,000 hours of speech. We cannot even think of collecting, but we can use them and adapt it, do the transfer training, learning to adapt to our language. And Dr. Deepak will talk about it tomorrow. So these are my last slide, summary slide. We talked about the statistical models for speech recognition. We said that we just looked at how speech sounds are produced, the articulatory phonetics, popular feature vector, MFCCs, and the popular model till about a decade ago was the Gaussian hidden Markov model along with the Gaussian mixture model. And not only do we need acoustic models such as these acoustic models, but also language models to take into account the characteristics of the different languages. And to build a speech recognition system, you require linguistic resources, speech data, transcription, transgenetic tree, toolkits. We don't write all the code, we use the toolkits, completely going toolkits such as Kaldi, ESPnet, and so on. And we can also use pre-trained models. So end-to-end RNN pre-trained model sequence modeling, Dr. Deepak will talk tomorrow. So that concludes my talk. I still have 4 minutes. So that's where I end. And if there are any questions, I will refer to that. Okay, let me, thank you.
Thank you so much, sir. Am I audible, sir?
Yes, you are audible.
Yeah. Thank you so much, sir. Yeah, I really don't have words to explain how wonderful the presentation was. Okay, so my experience is not on speech processing, but yeah, personally I enjoyed it, and the illustrations also were really good. And yeah, I'm sure that some may not be all, but some of the participants will get benefited from this wonderful presentation. So these are my opinions, but now actually I would like to consider taking questions from the audience.
Yes, Dr. Reddy, Sasi Kant Reddy.
Yes, Sasikant, you have raised your hand. So if you have questions, please go on. No, others also, yeah.
Any other question?
Yes, anything you want to ask, either questions or feedback, whatever may be.
Yeah, I know this was a little long talk compared to Matthew's, Dr. Matthew's talk. Dr. Matthew went a little more quantitative, I went a little more descriptive. Maybe my age is catching up. I spent time highlighting on concept. So, okay, I guess that is it. So we will have the presentation continuing the same stream tomorrow at morning. Dr. Deepak will continue deal more with the sequence model. Maybe we should end this session.
Okay, so participants.
Okay.
Okay, sir.
See you tomorrow. We will come back tomorrow morning and attend this session.
Yes, sir.
Thank you.
Yeah, thank you, sir. Once again, yeah. Thank you so much.